In these slides, I will show my research project work, and I will explain the challenges I tackled during the development and the solutions I applied. I started in 2015. At that time, I was inspired by the DARPA Robotic Challenge to build a low-cost humanoid robot. My goal was to develop a do-it-yourself platform that acts as a test bed to educate students about robotics using 3D printing and off-the-shelf controllers. But since 3D printers were not easily accessible at my university, I had to buy a small 3D printer kit from a startup company called PrinterBot. It was a hard task to assemble the kit, configure it, and calibrate it before start printing. I printed the first humanoid robot design using the Darwin Open Platform. After printing the parts and assembled them, I noticed some of the design limitations, like the size of the robot, the space for the embedded controller, and the degree of freedom. So, I switched to another design that has more degree of freedom, but also it has bigger parts that cannot be printed by small 3D printer. When I tried to print large parts in small pieces, it creates weak links at assembly, and the parts breaks easily. So, I bought another 3D printer with larger printing volume. The second design was from Puppy Humanoid Robot. It has a good sturdy design, but it lacks the space for the embedded controller. Also, it focuses on functional morphology. However, it's a good start point for my project. As for the embedded controllers, I started with single board computers SBCs, such as Raspberry Pi, Beagle boards, Intel Edisons, and Odroid boards. Then, support that with microcontrollers board like Arduino. I also been able to implement my design in the robotics simulator VRIP with the help of open source software community. Now that I have the platform built, I'm ready for developing the control library. Here you can see the SBC attached to the back of the robot via Scotch tape. I benefited from wireless connectivity in SBCs to monitor the robot's status. The small feet of the robot puts a huge load on motors in the lower limbs just to lift the weight of the robots and keep it balanced. So I couldn't develop a proper locomotions for the legs. To solve this problem, I used the simulator to write the motions control code and design the set action that consists of multiple joint motions. I tried different strategies to keep the center of gravity at the optimum spot, but I failed. Because the design in the simulator does not incorporate sensors, the only feedback available is the actuator's angles. After several tests, I get close to perform the proper action, except that simultaneous motor movement affects the robot's stability. It turns out controlling joints in sequence prevent the center of gravity from changing rapidly, and thus the robot remains balanced. Finally, I succeeded. And here is the optimum control sequence. While the control library is almost ready, the hardware has different problems. Low processing power held back the system from controlling and monitoring the motion at the same time, let alone analyzing sensor inputs and make decisions. Here, I have compiled a little demo using Raspberry Pi to show its capabilities and limitations. Note that everything is running from the Raspberry Pi, the motion control, the LCD screen for the face, the sound for the demo, and the networking for monitoring. All of that causing jitteriness in motion.
Hello and welcome. My name is Ezzo. I'm a humanoid robot developed using open source tools and software. The goal of my development is to help students and researchers, even independent developers and hobbyists alike, to learn making and programming humanoid robots. Also, I offer low-cost test bed for robotics and mechatronics. Now, anybody can build me and start developing. All you need is a 3D printer, motor, and some electronic components. Thanks to open source community for the tools and software that help creating me, and special thanks to NREA Research Institute in France for the mechanical design puppy humanoid within Puppy Project and for the Bipod framework in Python. Also, thanks to engineer Turki Abdulaziz from King Abdulaziz University who developed the task-oriented humanoid control library Ezzo Humanoid. Thanks to all of you.
Thus, I decided to build a distributed system using SBCs for processing and Arduino for controlling. Unfortunately, 1 year later, I lost my father and I had to take care of the family, so I decided to put the project on hold. For months, I struggled to get back to work on the project, but I have managed to redesign the lower limbs with enclosure to fit the distributed control on board. Finally, I have decided to stop the project because it passed the allowed submission period.